Alright, welcome back. So this video is dedicated for grade 11 advanced and grade 12 advanced, as both of them are starting this term studying this chapter, fundamentals of light, and starting with this section, illumination. So here we go with this part. So starting with this paragraph where light path. As humans, we already gather information using the 5 senses. Most important one, we believe that the eye is the most important. Because why? Because it gather more information than the others. So here we read this part. So light seems to provide greater variety of information. So that's why as human we rely on our eyes the most among our 5 senses, and that's why it's worth to study light, because it's providing us this information to our eyes that's received by our brain, and it's translated to information. All right, so let's start with this small information that we already know that the path of a light or for a ray, the path of the light is a straight line. We can see this through multiple examples. One of them is this one, as we see here in the picture, where light going into straight line, or we call it a ray, going into a straight line every time it passes through the clouds. All right, we see this also, the straight line of the light when we turn on a flashlight. But wherever we have an object standing between the source of light and the screen, whenever we have an object in the middle, this object creates a shadow. That's what we are reading here. When your body blocks the sunlight, so you see your outline in a shadow. That's what do we see here. That's the shadow or the absence of the light on the screen. All right. Next, so in general, for an object to be visible, this object have first to receive the light. You see, receiving the light under multiple colors, absorb some of them. So as an example here, the leaf, the tree leaf here. Why having the color of green? Because it absorbs all the colors and reflect one color, which is the green. So our eyes see the leaf as having a green color. Wherever in physics, this object, the leaf, absorb all colors but reflect one, which is the green. So we read together. So for an object to be visible to you, light must travel from them in a straight line to your eyes. As we see here, the green ray travel from the object or reflected from the object, wherever it is. Here in this case, it's the leaf, and it travels in a straight line to our eyes. All right, we continue. So coming with the ray model of light. So here with the ray model of light, it's a early model where scientists start to study or to learn more about the behavior of lights. Okay, so each arrow. Okay, so each arrow here in this picture, as you see, each arrow represents a ray of light which travel in a straight path until it reaches a boundary. So imagine we have a source of light. This source of light here in this example, it's the light bulb. It's sending a ray of light. So imagine here we draw that. So in every direction, the light is sending a ray. So this is an infinite number of rays. As you see here in this picture on your left, we have an infinite number of rays. Okay, so that's what we call as the ray model of light. So each arrow represents a ray of light which travel in straight path until it reach a boundary, until it reach a wall, it reach our eyes, wherever that boundary is. All right. So also we can see here, it's sending light in all directions. Okay, in all directions. So the lights start from the source and travel in all directions. You can imagine this as a 3D. So not only to the right and left, up and down, in all 3 dimensions, creating like a bubble of light. All right, so that's a quick introduction about the ray model of light. So when this light or when this ray start from the source, travel, going his path and reach a boundary, this ray of light follow or go through several behavior when it reach a boundary. So it could be as a reflection, as you see here. The light start from here. Okay, imagine this as a laser beam or laser light. So it starts from here, reach the boundary. This is the boundary. Imagine like a mirror or a glass, and then this ray of light is reflected back. Okay, it's still on the same medium. Okay, another behavior of light is called the refraction. So by the way, this is what we call by reflection. So this is the reflection. So this is the reflection of light. Another behavior for the same beam of light. So when starting from one medium, it starts from here, reach the boundary at this point, but then it's not reflected, it's refracted. That's what you call by refraction. Okay, it changed its direction. Okay, that's what you call by refraction. Refraction. So we have till now we have 2 behaviors for the light. First, it's the reflection, where the light stay on the same medium, doesn't intervene or enter the other medium. Okay, stay in the same plane, same medium. Yes. The other behavior, when the light penetrate, okay, the other medium, but it's changed a little bit the direction. As you notice here, the light doesn't go into straight line. It's deviated from its main direction. So this deviation is called the refraction with an A. Refraction of light. So we continue with the source of lights. So we have here on our planets, we have multiple sources of lights. The main thing or the main source of light, it is considered as the sun. The sun is the main source of light on our earth. Another source of light could be the candle or diodes or the torch or electricity, we can tell, that send light. So these are called luminous sources. So all of these 3 are luminous sources. Yeah, because they generate the light, they send the light. So all these 3 are called luminous sources. As you see here in this picture, we have the sun. Okay, imagine this as the sun. We have the planet, our planet Earth, and we have the moon. So who's the luminous source among all of these 3? It is the sun. The sun is the luminous source. Here is the sun. All right. So this is the sun sending the light. It's the source of light. What about the moon? Look at the moon. Something interesting happening here. So the moon receiving the light, but it's reflected back to the earth. So it's receiving the light. It's not a source of light itself. The moon is receiving the light and then reflected back to the earth. So that's what we call by illuminated. So the moon is an illuminated sources. Okay, it's one of the illuminated sources because he's not generating the light by itself. He's receiving it from the sun and the moon reflected back to us, to the earth. That's why we see the moon as lit object. But the light is not coming from itself. It's reflected from a luminous source, which is the sun. Again, the moon is called as an illuminated source. We continue. Okay, we continue with the ray model of light, talking about transparent, translucent, and opaque object. Let's clean the board now. So we continue the ray model of light, but talking about light and matter. So We continue talking about the objects. We have three types of objects when talking about the light and their behavior when hitting such objects. So either the object is a transparent object. Let's imagine we have a transparent object like here. So all the light starting from the source, all the light passes through. So this is called a transparent object. So this is a transparent. We can see through. Transparent. Okay. What if the light is blocked? We don't see, no light's passing. You see, no light is passing through. Okay, so this is called what? This is called as an opaque object. As you see here, can you read? This is an opaque object. Okay, this is an opaque object. What if 50% of the light passing through? Not all the lights passing through, and not all of them are blocked. So some of the light is passing through. So this is called by translucent. Translucent, SCENT. So this is a translucent object, as you see here with the lenses. If you can see the car all the way through the lens, so the lens is transparent. If we cannot see through, like a wooden table or a wall, so this object is called an opaque object. What if we see but not 100% clear? So this is what we mean by a translucent lens or object. All right, now starting the second part of our chapter, talking about the quality of light. All right, so the quality of light depends on few things. So in this paragraph, they are telling us that the quality of light depends on, okay, so we have three main factors here, okay, three main things. We have the quality of light that the flashlight produces. So the quality of light, if it's weak, as here in this picture, or it is strong as this picture. So this is the quality of light or the brightness, all right? So this is the first parameter, first factor. We have the distance between the light bulb and your eyes. Okay, so every time I am far from the light, so of course we are receiving less light. Every time you are close to it, I'm receiving more information, more light. And the angle at which the light rays hit your eyes, and the angle, okay, at which we are looking at the light. So these are the three main factors. Again, they are the brightness of the source itself. It is the distance between me and the source, and every time you are close to the source of light, you are receiving more light, and every time you are far, of course, you are receiving less light, and at the angle that we are looking at the light. So these three factors that affect the quality of light in a light system. We continue talking about, first of all, the luminous flux. Okay, so the luminous flux, okay, here we'll make a small table that will continue with us till the end of this video, I think. So we have the luminous flux, okay, it's the rate at which the bulb or a luminous source produce light energy. So it's about the source of light, okay, it's about the light bulb. Okay, so imagine this as a source of light and sending light all around. Okay, so then we are talking about a luminous flux. Okay, the unit of the luminous flux, or again, first it's the symbol having P as a symbol, but the unit is lumens, LM. So let's write it here. We have the luminous flux. Symbol is P and unit is lumens, LM. So this is the unit, LM. All right, and again, remember, it depends only on the source of the light. Okay, the amount of light energy sending, okay, remember, light energy sent by the source of light, whether it's a light bulb, it's a star, it's the sun, whatever it is, even a candle. So then we are talking about a luminous flux with the symbol is capital P and the unit is LM. We continue. Here we are talking about the illuminance. Illuminance is about how much light is received by objects. So we are not talking about the source anymore. So illuminance is the light, is the luminous flux falling on a given surface. It's the amount of light received by an object. It's not about the source anymore. It's about how much we are receiving light. So let's write it here. So talking about the illuminance. Okay, the symbol of the illuminance is E, as you see here, illuminance, having the symbol of E. Okay, and the unit is lux, LX. LX as the unit. So let's read it together. The luminous flux falling on a given area, surface area, at any instant is called the illuminance and having the symbol of E. All right, which is equivalent to the lumens per square meter. Okay. All right, so either the unit is Lx or Lm per meter square. All right, so this is about the luminous flux, then about the illuminance. We continue. Okay, here we are taking an example. Imagine we have a fluorescent bulb, okay, having a radius, okay, having an illuminance of the sphere inside of a radius of 1 meter. Okay, so we are what's given here in this example, that the source, the luminous flux of the source is 1750 Lm. So luminous flux talking about the P. Okay, so how we calculate the E? So because here they are asking about the illuminance. So how to calculate the illuminance? So we bring this value about the luminous flux and we divide it by 4 pi r square. Okay, it's 4 pi r square. It's the area of a sphere, and that's how we calculate the illuminance E. Okay, so the illuminance is 139 lux. Okay, every time, this is because r equal 1 meter. Every time we are going further, let's say 2 meters, of course this value will get weaker or less. Next. Okay. Yes. So, as we see here, imagine we are talking about 3 meters radius. Okay, so the illuminance will be equal 15.5. You see, the value is getting weaker and weaker every time. From 139, now we are talking about 15.5. Okay, strike each square. So let's read together. As the light rays spread out in a straight line in all directions from the point source, the number of light rays that illuminate a unit of an area decrease. Of course, as we see here, let's look at this graph, by the way. We have a source of light. Every time you are far from, imagine this is 1 meter, this is 2 meter here in the middle, and here it's 3 meters. So you see the intensity of the light or the brightness is getting weaker and weaker every time we are far from the source itself. All right, we continue. So, talking about now the last parameter when discussing the quality of light. So we first discussed the luminous flux, then the illuminance. Now talking about the luminous intensity. Okay, here in this chapter, let's consider the luminous intensity as I, capital I, and the unit is candela, okay, CD. Okay, it's about CD. So let's read it. So some luminous sources are specified in candelas, CD. So this is the unit of the intensity of the light. So why we are talking about luminous intensity? This is because it's about before reaching the object, which talking about the illuminance E, before reaching that, there is something happening here in the middle. Okay, so the light going in one direction is going into a straight direction. That's why we have to talk about luminous intensity, because in a real application in life, when I turn on a flashlight, I don't want the flashlight to go everywhere in the room. I want it to go in a straight direction, into a specific direction. So when talking about a specific area or a specific direction, then we have to talk about luminous intensity. So the equation of the luminous intensity, it's the P, okay? It's the lumens one, the equation of the intensity. Let's write it down. It's not written here. The luminous intensity, it's about P, okay? It's about the luminous flux, okay, divided by 4 pi. And that's what do we mean by I. And the unit, of course, it's candela. So the intensity of the light is, it's the luminous flux P divided by 4 pi. All right, and by the way, how to calculate the illuminance E? E, it's equal to also P. It's similar to the intensity, but instead of 4 pi, it's about 4 pi multiplied by distance square or r square. I hope to keep this till the end of our session, because we'll use it later on in our application. Surface illumination, we are approaching the end. Yes, I think so. So the surface illumination, every time you increase the how to control the surface illumination, by the way. Okay, either as you see here in this picture, the boy is starting to look straight into the book because cannot read it, it's not visible. So either we decrease the distance between our eyes and the object so we can see better, okay, or either we increase the luminous flux. Okay, so let's read together. So you could move your eyes closer to the light. So this is one thing. So this means by decreasing the distance between the eye and the light source, okay, or we increase the luminous flux, okay, or we increase the light intensity of the source of the light. Okay, this is the equation that we already discussed here. So E, which is the illuminance, is equal to P, which is the luminous flux, divided by 4 pi r square. Let's solve this. After discussing all these equations, let's try to solve this problem. All right, so we have a table lighted or attached with a light. So what is the illuminance on your desktop if it is by a 1750 lamp, lumens lamp, and it is 2.5 meter from your desk? So how to calculate in this case the illuminance E? Okay, so E will be equal, we are using this equation here. So E will be equal to P, okay, which is the luminous flux, and it's given, by the way, 1750 divided by 4 pi multiplied by r square. The distance here is given 2.5 squared. All right, and the answer is, let's do it. So P again is 1750 divided by 4 pi multiplied by 2.5 squared. And the answer is 22.22. Let's consider 3, okay, lux. Okay, the unit is lux. All right, that was for this part. We continue. Let's clean the board first. All right, so let's continue with question 1. So a lamp is moved from 30 centimeter to 90 centimeter above pages of a book. Compare the illumination. Okay, so talking about E, illuminance, on the book before and after the lamp is moved. So on the first position it was at 30 centimeter and then moved to 90 centimeters. So let's calculate E first. E on case 1. So E, I will call it E for 30 centimeter. Okay, it's equal to P over 4 pi r square. Okay, so that was for the first position. And they are asking us to compare. Alright, so it's about comparison. It's not about calculating, we are comparing. And usually when we compare, we do the division. Okay, it's not about subtraction. If they ask for the difference, then we do subtracting. But when asking for comparing, so we have to do the ratio of the two. Okay, or the division between the two values. So the second one is for 90 centimeters, which is equal to P, same, for over 4 pi 90 square. So because they ask for comparison, so we are doing the ratio between the two. So let's write, let's say E30 over E90. Okay, so then what we conclude, what do we have? E30 is equal to P, okay, over 4 pi 30 square over E90 is same, it's P over 4 pi 90 square. So here we can simplify things. We can, because P is the same. Okay, P never changed for both. Okay, so P and P will be simplified. Also we can simplify 4 pi and 4 pi. So what we are getting here, we are getting this value. So 1 over 30 square over 1 over 90 squared. Okay, so in that case we have to flip, because we have double division, so we have to flip the values. So E30 over E90, it will be equal to 90 squared over 30 squared. So when doing the division, it will be equal to 9. So E30 centimeter over E90 centimeters is equal to 9. So what this means, what the 9 value means. So it means that E30, if we multiply, so we are getting E30, okay, will be equal to 9 times E at 90 centimeters. Okay, so this means that the illumination at 30 centimeters is 9 times more powerful, having more values, 9 times more powerful than the illumination at 90 centimeters. It's 9 times more powerful. We just move it from 30 centimeters to 90 centimeters. So the difference here is like 60 centimeters. But in terms of illumination, it's 9 times more powerful. All right. Let's move now to question number 2. Of course, we have to clean the board. And now with question number 2, we have to draw here. We have to draw a graph of illuminance produced by a lamp, okay, with a luminous flux. Remember, the luminous flux is P of 2275 lumens at distance from 0.5 to 5 meters. So we have to draw a graph. So what do we mean by graph is we have to draw the x-axis. Let's put it here, somewhere here. So in terms of x-axis, it's about the distance, okay, r, and the unit is meter. Okay, so, and on the y-axis, we'll talk about the illuminance E, okay, which the unit is lux, LX. All right, so I'll choose like I'll not choose all the distance from 0.5 to 5 meters, but I'll take few positions. So let's take it first at 0.5 meter. So this is 0.5. I'll choose as well 1 meter. 1 meter. I will take as well 2 meters. So this is 2 meters. I'll calculate, the luminance at 0.5, at 1 meter, 2 meters, and let's say 5 meters here. So I choose 4 values. Okay, I choose 4 values for the luminance. So now let's calculate the luminance using this equation here. So let's calculate the luminance at 0.5 meters. So E for 0.5. So the equation is P, again P over 4 pi r square. P is given, it's 2275 over 4 pi r square. Here r square is 0.5. So let's do it on the calculator. So 2 divided by 4 pi, and the answer is 724. 724 lux. Okay, I'll do the same thing, the same scenario for E 1 meter, and the value will be equal to 181 lux. Okay, 181. I'll do the same thing for 2 meters, E for 2 meters, and then at the end we put the values on the graph. So E for 2 meters, it's equal to 45 lux, and E for 5 meters, the last value, it will be equal to 7.2 lux. So now let's put the values on the graph. So for 0.5 meter, the value were way too high. It's 700. I'll consider it here, but it's way higher than that because it's 724. It's very big value. The other value for 1 meter, it's 181. I'll consider it here. I'll consider it somewhere here. It's a little bit less than that. It's 1 meter, so I'll consider it here. Okay. The other value here, it's 45. So if this is like 180, 45 for 2 meters, it's somewhere here. Okay. The last value is 7.2. So remember, we are going from 724. Now it's 7.2 only for 5 meters. So it's nearly zero. It's somewhere here. So if you draw the graph, it will go from up. It's something like that. That's how the light is reduced exponentially. Okay, it's not going down straight line. It's going following this graph. Okay, so these are the 4 values. Of course, you can choose more values, but I pick these 4 values to represent the graph that we are having or we drawing here in question 2. Okay, starting with question number 3 here. All right, so we have a 64 CD or candelas, point source of light 3 meters, the given is 3 meters, away from a painting. What is the illumination? So illumination, we mean by that the E. We have to calculate the E of the painting. So let's write the equation of E. So E is equal to P over 4 pi r square. But we have a small problem here. R is given. R is 3 meters already, it's given. But the problem here is with P. What is the value of P? How to calculate P in this case? So if we find P, we divide it by 4 pi r square and then we calculate E. So the question here also is to calculate P. What is P? So here we have to use this equation. Okay, remember the luminous intensity I, which having the unit of CD, is equal to P, okay, which is the luminous flux over 4 pi. So here the unknown is the P, the capital P. So how to calculate P in this case? So P will be equal, by referring to this equation, so P will be equal to the luminous intensity multiplied by 4 pi. Okay, multiplied by 4 pi. Alright, so the luminous intensity is given, it's 64 candelas. So it's 64 multiplied by 4 pi. And the answer here in this case it's 804. 804 lumens. Okay, so we calculated so P is given now. P is already calculated, it's 804. So now so we have to replace it in equation 1. So this is equation 1. So we replace in equation 1. So now the equation will be E equal P, which is that value 804, divided by 4 pi multiplied by r square. R square means 3 square in this case. So let's do the math here. So the answer is 7.11. It's 7.11 lux. Okay, and that's how we calculate the illumination for question 3. One of the most important questions because we are combining two equations. Equation of the luminance and the equation for the luminous flux and the intensity as well. Let's move on. All right, so let's discuss now, time for to discuss question number 4. So a screen is placed between two lamps so that they illuminate the screen equally. Illuminate the screen equally. What this means? Illumination. So we have two light bulbs. Each one is providing its specific illumination, but both of them are equal. Both E are equal. So what can you write? We can say here E1, because of light 1, is equal E2 for light number 2. As shown in this figure, the first lamp emits a luminous flux of 1445 lumens, which P, and is 2.5 meters from the screen. As you see here, this light is generating 1445 lumens, and it's 2.5 meters from the screen. The other light bulb is generating 2375 lumens, but the distance is not given. So the question here, what is the distance of the second lamp? So this is the question. We have to calculate R or X, okay, whatever you call it, or D sometimes, doesn't matter. So here for this light bulb, the lumens is given and the distance as well. For the second one, only the lumens is given, whereas the distance is not. So how to do that? And don't forget, the most important sentence in this question is they illuminate the screen equally. Okay, so this sentence, illuminate the screen equally. So we can start solving this question by saying that E for the illumination for the first light bulb is equal the illumination by the second light bulb on the screen. Okay, they are both sending the same illumination or received the same illumination by the screen. So what can you say by E1? E1, of course, it's P over 4 pi r square. I will call it r1 square because we have two distances here, so I'll call it r1. It's equal this is P1 as well, P2 by the second light bulb over 4 pi r2 because the second distance squared. Okay, so that's the main equation. So what can you say here? P1 is given, it's 2375 divided by 4 pi. Here is the unknown, so r1 Okay, I will keep it r1 squared. Okay, or you can put it as x because it's the unknown. It's equal. P2 is given as well. What's the value of P2 again? It's 1445. Yes, it's shown here. 1445 over, also the same thing, 4 pi. Here distance is given, it's 2.5 squared. So here you can do the shift solve and simplify 4 pi on different on both sides, and you get that x is equal, but after doing the simplification, you will get that x or r1 is equal to, after of course doing the square root as well, it's equal to 3.2 meters. And this is logical because as you see here, if you compare the distance from the picture, this is 2.5, is short, so the distance of this light bulb have to be bigger than 2.5, which is the case here. It's 3.2 meters. All right, so that was about question number 4. All right. We continue with the question number 5. So, what is the illumination on a surface that is 3 meters below a 150 watt incandescent lamp that emits a luminous flux of 2275 lumens? So again, we refer to this equation here. So the distance is given, 3 meters, luminous flux is given, and they're asking for what is the illumination. So E is the unknown. So I'll write it here. E is equal to P over 4 pi r squared. In this case, it's 3 meters, so it's a 3 square. So P, which is 2275 over 4 pi r square, which is multiplied by 9. And the answer in this case, it's 20.1 lux. Okay, that's the answer for question number 5. All right, let's move on to question number 6 now. So let's start solving question number 6. So we have a public school requires a minimum illuminance which is 160 lux. So let's write the given. So require a minimum illuminance of 160 lux. Okay, at a surface of each student desk. An architect's specification called for a classroom right to be located 2 meters above the desk. So distance is about 2 meters above the desks. What is the minimum luminous flux? Again, luminous flux is referred to as P. So P is the unknown. So okay, that is the light must produce. So what equation that combines all of these 3 parameters? Of course, we are talking about that equation. So where E equal P over 4 pi r square, but in this case, in this question number 6, what is the unknown is P. So we can say that P all the way is equal to E multiplied by 4 pi r squared. So E is given, it's 160 multiplied by 4 pi multiplied by 2 to the power of 2, which is 4. So in this case, let's use the calculator. It will be equal to 8,000. So it's 160 multiplied by 4 pi. Yes, it's 8,442 lumens. That's the minimum requirement for this public school, for the lights above the desks in this public school. All right, we continue. All right, with the question number 7 now. Same. It's close to question number 6. Same, we have a local public library is planning to remodel the computer lab. The contractors have purchased a fluorescent light with a rated luminous flux of 1750 lumens. So let's write the given. So the P in this case, lumens. Okay, the desired illumination on the keyboard is 175 lux. Okay, E also the desired. Okay, this means the minimum. Okay, 175 lux inside the library. So assume a single light or single lamp luminance each keyboard. What distance above the surface should be the lights be placed to achieve the desired illumination? So what is the distance? So they are asking for R. In this case, R is the unknown. Okay. Let's tackle the first question first. So again, what distance above the surface should be the lights be placed to achieve the desired illumination? So we need this illumination to be achieved 175 above each desk. You know, in the libraries, the lights are not that powerful. Okay, but they have minimum requirements, which is in this case 175 lux. So what or how to calculate R? Again, we refer to this equation. So let's arrange it again. So in this case, R square will be equal to P over 4 pi multiplied by E. So P is given. It is 750 I mean, over 4 pi multiplied by 175, and the answer is and the answer is 0.79. But don't forget it is squared, so we have to do the square root of this value. So you have to do the square root of this value, and you got it's around 0.89, or I will consider it as 0.9 meters. It's 0.9 meters. Okay, 0.9 meters. So this is for the first question, the first part of this question number 7. Okay, so we continue. If the contractors had also already purchased fixtures to hold the lights that when installed would be 1.5 meter above the keyboard. It's 1.5 meter. So it's way above this value. It's supposed to be maximum. It's supposed to be 0.9, the light from the desk. Now the contractor is saying we have to fix the light at 1.5 meter. So it's way too above this value. Okay, above the keyboard surface. Would the desired illumination be achieved? Of course no, it will not be achieved, because every time, remember in the beginning of the lesson, every time the distance is bigger, so we are receiving less light. Okay, here they are fixing the light at 1.5 meter, whereas it has to be at 0.9 meters. Okay, would the desired illumination be achieved? No, of course no. If not, would the illumination be greater or less than desired? Of course it will be less than desired. It is less than desired because we fixed the lamp way above 0.9 meter. So the light or the illumination will be less. The luminance, E in this case, will be less than required. So what change in the light in the lamp's luminous flux would be required to achieve the desired illumination? Okay, so asking for a change or modification. What a change in the luminous flux? So of course we have to bring a bigger light or a more or greater light bulb, because remember the distance is higher, 1.5 meters. So we have to bring a bigger light, okay, than what is required here. We have to bring or buy lights that's, I think, like around 200 lux or above, because remember the distance is 1.5 meter. It have to be around 0.9. Great. Okay, we continue. the last part of, okay, let's clean the board, and we reach the last part of our lesson. Okay, so the speed of light. So light, from the beginning of humanity, was a mystery. Okay, it's so hard to understand light, and it's exactly the speed of light. It was a mystery all the way down through the centuries. So, but what do we know at least? Okay, what was known at least, that the speed of light is much faster than the speed of sound. Okay, speed of sound moving at a speed of 340 meters per second, whereas the speed of light, we'll see how much or how greater it is. Okay, so actually measuring the speed of light was not an easy task in the 17th century. So in the 17th century, we have a genius called Romer, who thought out of the box. So all the previous experiments were trying to measure the speed of light inside the Earth. And you know, Earth is too small in compared to the distance the light traveling. So he think out of the box, out of the Earth, and he measured the light, if you see here the graph, from the Earth itself. You see the solar system here, and this is the Earth at different position, 1, 2, 3, and 4. So he measured the speed of light from the Earth to Jupiter. Okay, and not the Jupiter exactly, it's the moon of Jupiter. It's called Io. Okay, it's called Io. And he measured using his own tools and telescope, and he measured the time it's taking the light to go from position 1 to the moon itself. Okay, you can't see, okay, because of the picture, but to reach this position. Okay, and then waiting the Earth to reach the third position, and do the same measurement here to reach the moon. Okay, after doing one cycle around Jupiter. So he noticed some difference between the two paths. Path number 1, where here we have a value of plus 30 seconds, or I mean minus 30 seconds, whereas in the other path he is measuring the light as having plus 30 seconds in compared to the value known at the time. So here there is difference in values of 30 seconds between the first path and a different path. This is due of the light traveling another distance. So because light is traveling a much bigger distance, so it required more time logically. All right, so that was his conclusion, that light is traveling too fast, and he calculated a value. It was at the time interesting value, but it was not accurate, but it was, we can't deny he's a genius scientist, Romer, and his first attempt to measure the speed of light using the moon of Jupiter. So he got two different values. One is minus 30 seconds in compared to the time required for the light to travel from the Earth to Io, and then the value plus 30 seconds when the Earth is on position 3. So again, this is due of the because the light is traveling less distance here, so of course the time will be less. All right, so that was a first attempt or serious attempt to measure the speed of light. We have another attempt also by Michelson and Morley, or Michelson measurement also, but this time he's using mirrors to reflect light between two mountains. So, and two mountains, I think they mentioned where, I think in California. He picked two mountains, he chose two mountains, he put mirrors, he is using mirrors. Okay, so the light, it's the incident light goes and then reflected back. Okay, also using his own instrument to measure lights using mirrors. Okay, and he got more precise value in compared to Romer, he's the previous scientist. Okay, so Michelson and Morley, they got a more precise measurement in this case, and they are approaching the value of 3 by 10 power of 8 that we'll talk about in a bit. Okay, So after this experiment by Michelson measurement, okay, we got the value of c. So c is the constant of light. Every time we are talking about speed of light, we are not saying s anymore. It's not s anymore. Okay, it is c. C, constant of light, which is 299,792.458 meters per second. So instead of saying all of these numbers, so we write it as scientific notation. It's equal to 3 by 10 power of 8 meter per second. Or it could be written as C equals 3 by 10 power of 8, or sorry, power of 5 kilometers per second. Okay, so this is the speed of light. Speed of light, which is of course greater than the speed of sound when compared to the speed of sound, which is only 340 meters per second. Here we are talking about gigantic values, 10 power of 8 meter per second. So because of such big numbers and because of the gigantic scale of the universe, as you see here, we are not supposed to study or to measure distance between planets in kilometers. So we have to find different ways to measure distance between planets and galaxies. And this is what we are talking about, the light year. Okay, what it is, the light year. Okay, the light year. So light year, what do you mean by light year? So let's write it down. So the light year. So again, we are measuring distance using a new parameter called a light year. So what do we mean by year? Year, again, it's 365 days, right? Multiplied, but let's consider every day by 24 hours, multiplied by 60 minutes, multiplied by 60 seconds. Okay, so this is the time of the year in seconds. Okay, that's year. Okay, what about the light? We just mentioned that the speed of light is 3 by 10 power of 8. So it's 3 by 10 to the power of 5, but this time it's kilometer. I choose to go kilometers per, just kilometers, all right? So because I want the end unit to be in kilometers. If I want the end unit to be in meters, I pick 10 power of 8. So when calculating this value, we got this number, which is 9.46 by 10 power of 12 kilometer. So again, you can do it on the calculator and you get this value. It's 9.46 by 10 power of 12 kilometers per year. So that's the distance the year is covered. So you know what do you mean by 10 power of 12? It means 1,000 billion. 1,000 billion kilometers per year. So this is something extraordinary. Okay, this is how we measure the distance when talking about the universe or about such gigantic scale. We are just talking about light year, which is again 9.46 by 12 kilometers. I think that's it for this lesson, and see you in the next one talking about the wave nature of light.